So this is going to be a video on 8.5, which is testing a claim about a mean when you do not know the population deviation, also known as sigma. This is not going to be very different from the last one we did because all that's changed is that we don't know sigma, and just like with confidence intervals, when that happens, we simply use the sample deviation, and then we use a t-score instead of a z-score. That's the little subtitle there. So again, first off, as a reminder, always and forever, these are the requirements that we're using. It hasn't changed since we first started talking about them. Main things being, it has to be a simple random selection. So again, you have to make sure that you're selecting people actually randomly. You're not giving undue credence from one population to the next. You obviously don't know the population deviation, and the population has to be either normally distributed or you have to have a sample size of bigger than 30. Okay? Again, same things we've been talking about. So here is our new test stat formula. So remember, our test stat in this case is actually a t-score, not a z-score, because we do not know the standard deviation of the population. So we use a t-score to help us give a bigger variance, account for the less knowledge that we have essentially. But it's mainly similar from the last one, right? We have the sample average, which is x bar here. We have the population average that we're testing, which is the mu here. And then we have the sample standard deviation and the total number of values that we're looking at, the total number of your sample size. So remember, reading a t-table is different than reading a z-table. So this is kind of recapping how to read a t-table in case you've forgotten. Remember, we have the degrees of freedom, which is basically n minus 1, the number of values you have minus 1. The table does not give negative values, so if you were to get a negative t-score, you would have to use the positive version. I'll just say positive from the table. So remember, it is symmetric. So if you get a t-score of negative 1.5, then on the table, you're going to look up a t-score of positive 1.5. And because it's symmetric, you'll get the same area behind the curve anyway. So it's okay to look up the positive versions even though they're not listed, or even though you might get a negative version answer. The table does not give p-values in the same sense that the z-score does. We'll talk about this in a second here, but we cannot look up p-values as easily as we could last time. The top of the table tells you which test to use. Remember, we kind of looked at that briefly in the last videos, but you have your area and one tail down here, and your area and two tails up, or sorry, vice versa, my bad. Your area and one tail up here, and your area and two tails down here at the very top of the table. That will help guide you as to what test you're doing as well. And remember, the table in this case assumes the values are to the right of the t-value, not to the left like in a z-score. That's because the t-table uses the positive values only, so it goes from the right. It's not going to be too much of a difference because, once again, it's symmetric, so it's okay to go from the right because it's just going to be copied over anyway when we need. So that's a t-table in case you forgot. Remember, here's your degrees of freedom right here. And then here you have your area and two tails and area and one tail up here. Again, depending on whether you're doing a two-tail test or whether you're doing a one-tail test. So this will be used for left and right tails. This would be used for obviously a two-tail test. And then you have these t-scores in the middle. So these scores down here, these are your t-scores right in the middle column here. So all these values in the middle here, I kind of dipped over there, but all these values in the middle are your t-scores. Now, here's where your p-values are. Because remember, a z-score table has a p-value table. These right here are actually your p-values. And notice there's not a lot of them, unlike a z-score table. So when we're getting p-values, it's going to be a little bit different to do that with this. That's why sometimes using the traditional method, where you compare the critical value rather than the p-values, is a little bit easier for when you're testing a mean. But we'll get to that here right now, actually. So if you want to find the p-value from a t-score table, you often can't. So what you do is you give your best estimate based on where your t-score lies between two other values. So in this case, let's look at an example here. So let's say that we got a test statistic of 2.77, right? We ran our data, and we got that as my test stat. And the sample size was 20, significance level was 0.05, and the alternative hypothesis is that, it's not equal to 5. Okay, so we're doing a two-tail test, right? Find the range of p-values using the t-table, left, right, or 2. So what we do is we go back to our t-table. Now remember, we have n is 20, right? So we're looking at 19 degrees of freedom because one less than 20. And we're going to find out what scores is 2.77 between. So remember, our test stat, just to rewrite down here, was 2.777. So we're going to look for 19 degrees of freedom and figure out what scores is 2.77 between. Well, 2.77 looks to be about right between these two scores, right? 2.77 is less than 2.861. Oh, that's appearing again. Less than 2.861, but more than 2.539. So 2.77 is right in between these two values. Now, since we're doing a two-tailed test, because remember my claim was that it was not equal to, oh my gosh, that's just really bad. Let me try that again. I really do not know why it does this, to be honest, but it is supremely annoying. So remember, the claim was that it was not equal to not equal to 5, right? So it's a two-tailed test. So we look here and we look up into the area of the two tails because that's the kind of test we're doing, and we see that this p-value is going to lie somewhere between 0.01 and 0.02. So we'd say that the p-value for this test statistic, the PV, is, we don't know, but it's going to be somewhere between 0.01 PV and 0.02. It's going to be bigger than 0.01, but less than 0.02. It's going to be right in between the two. We don't know if it's exactly in the middle. In fact, it's probably not exactly in the middle because it's probably closer to 2.8 than it is to 2.5. But it's going to be somewhere between these two values. So once again, you can't get the exact p-value unless you use some sort of technology, which we'll talk about later on. But you can get a rough estimate, like a range between which two values. Now, let's say, for instance, that my test stat, let's say my test score was, once again, we're still working with degrees of freedom of 19. Let's say my test stat was 1.2. Okay. Well, if I look in this row here, 1.2 is all the way at the end here, right? So 1.2 is all the way over here. So in this case, I would look at it and say, okay, if as I'm going down this chart here, my area is getting bigger and bigger and bigger and bigger and bigger, right? So as I go from t-score to t-score to t-score to t-score to t-score, as my t-score goes down, my area goes up. So I would say that, well, 1.2 would probably be more than 0.2. So the p-value of this would be bigger than 0.2. I don't know how much bigger, but I know that as my scores are going down, my area, my p-value, is going up. So therefore, 1.2 should be bigger than 0.2. I don't know about how much, but I know it should be bigger than. And then similarly, if you have like 2.9, then you would say your area is less than 0.1 because 2.9 is bigger than 2.8, and as you're going this way, the areas on the top are going down and down and down. So you would be getting a p-value of less than 0.1 when you're going down this way, okay? Or 0.01 where you're going down to the left. So that's how you deal with the ends of the extremes there. Now again, because this is such a hassle, usually use the traditional method of testing rather than the p-value method because getting p-values from a t-score table is, I guess you can see, kind of tedious. So we'll kind of do that in our example here coming up. Just remember, once again here with negative z-scores, that you use the absolute value of it to find the p-value range. So it's nice and symmetric, so that's fine. But when you look up negative 1.5, remember you're actually looking up 1.5, not negative 1.5. And so don't think that you're all the way at the far end of the column there, when in fact you might be somewhere in the middle. So once again, just make sure that you're using the positive version of the score to look up, not assuming that there's a negative version hidden in there somewhere. All right, so let's get through an example here just to show you how it's done. Only one example in this video, just because that it's so similar to the last one. But again, I'll be here to do more examples if you really need. Okay. So in previous tests, balls were dropped from 24 feet onto a concrete surface, and we're measuring how high they bounced. So the first balls bounced 9.284 inches, we're assuming in the air. They sampled some new balls, 40 of them, and they found that the bounce had an average of 9.67. So they dropped the balls and they bounced 92.67 inches in the air. And the standard deviation was 1.79. So use a 0.05 significance level to determine whether there is sufficient evidence to support the claim that the balls have a bounce height with a mean different than 92.84. Okay, so we have two sets of balls. The balls we first tested had a pretty high bounce height, 92.84 on a concrete surface. These new balls only bounced 92.67. Now, our claim is that these new balls have a different mean bounce than the original ones. And right now it's kind of supported, right? Because look, they bounced smaller on average than the other balls. So you say, well, this average is smaller than this average, therefore they have to be different. But as we said, that's not necessarily the case. Maybe they're not different enough to actually claim any significant difference, right? Maybe this was just a fluke in a sense. So let's go ahead and figure out if we can test that. So I'm going to rewrite my data over here. So we have that the new average from my sample was 92.67. We have that the deviation from the sample, not the population, but from the sample that we got, was 1.79. And we tested 40 balls. And we know that the original ball height was 92.84. That was the original height of the balls we tested. And so my claim, if we go back here real quick, my claim was that the means are different. Now, it doesn't say bigger than or less than, it just says different, which means that we're dealing with a two-tailed test. We're dealing with a not equal to. So I'd say here that my null hypothesis is always equality. My null hypothesis is that they're not different, right? There is no difference. Everything's status quo. My alternative is that the average is different, so it's not equal to 92.84. And this right here, I'll put a little C here. This is my claim. This is actually what I'm testing for, right? So I'm either going to support my claim or I'm not going to have enough evidence to support my claim. All right, so let's go ahead and see what we have. So let's first get our test stat. If you remember, my formula was the average of my sample minus the average of my population from before over, or not the sum, minus my claimed average, right? The average of my claims here, divided by the standard deviation of my sample, 9, over the root of 40. I'm going to erase these random lines here because they're annoying me, and then I'm going to rewrite all that stuff again, which is equally annoying. There we go. Oh my gosh. Okay, we're just going to leave that one there. So if we tally all this out here, we end up getting a test stat of negative 0.6007. So let me write that a little bit nicer there because I kind of missed that decimal marker. Try that again. Come on. So negative 0.6007. So that's my test stat. Now I need to figure out whether that test stat conveys significance or not. And remember, my alpha was 0.05. That's what my testing significance is. Now, once again, I could try to get a p-value for this, but that's going to be kind of hard to do because, again, getting p-values from t-score tables is not nice. It'd probably be easier to convert this p-value into a critical value, into a t-score itself. Remember, a critical value is simply the z-score or t-score or chi-squared score of your significance level. That's all a critical value is. It's taking your significance level and making it into a t-score or z-score or whatever score that you can compare against your test stat. So we have 39 degrees of freedom, and then we're going to convert 0.05 in two tails to a t-score. So let me go back here and show you how that's done here. Okay, so we're testing for it in two tails, right? So we're testing it over here. This is my alpha that I'm looking for. Now I have, oh, I don't go down that far. Darn. Okay, let me make up a bigger t-score table here. Give me a second. There we go. All right, so we're looking up this alpha, right? And we have 39 degrees of freedom, which is not on here, so we're just going to use 40, right? And then we're going to see where they intersect. So 40 degrees of freedom, 0.05 is an alpha, means right here, 2.021, that is going to be my critical value, okay? Plus or minus that, but yeah, 2.021. So my critical value is plus minus 2.021. All this is representing is taking your alpha and converting it into a t-score that we can compare against my test stat. And so remember, we're going to kind of go traditional here, so we haven't done this in a while. So this is how it works. Picture a graph, and it really does help to draw these bell curves if you're having trouble doing this in your head. Let's mark my critical values. So here is negative 2.021. Here is positive 2.021. Okay, whoops. And then I'm going to erase those random lines because those are going to get in the way. Boom, boom, and redraw. I really sorry I have to do this, but it has to be done. Now, where does my, this is my critical region, right? My region, oh my gosh, my region behind the stuff, right? My region behind my critical values, that's my critical region. So where does my test stat lie in all this? Where does my test stat sit? Well, negative 0.6 would be definitely before negative, so if this is 0 right here, remember 0 is always in the middle, so there's 0. So negative 0.6 would be somewhere like, let's say, right here. It's a rough estimate. Negative 0.6. Okay. Well, it looks like my test stat, my negative 0.6, is really firmly within inside my rejection region, right? Or my fail to rejection region, right? My rejection region are these shaded areas there. If it was less than negative 2.02 or more than positive 2.02, then we'd be in the rejection region. But right now I'm sitting squarely in the OK area. So this test stat is not extreme enough to warrant rejection. So what we'd say here is we say we fail to reject HO. So we fail to reject the null hypothesis. We don't have enough data. The data that we're given is not extreme enough to reject the fact that nothing's changed. Basically, the chance that we got lucky and got a smaller average is too high. And so since my claim was the alternative, but I failed to reject HO, I would say that the data does not support the claim. Okay? The data does not support the claim because it's simply not extreme enough to warrant support. Right? We would need much more extreme data to say that, because we're not even close to my critical values here. And so when it asks, does it appear that these new baseballs are different? Well, no, because if they were different, then we'd have enough evidence to reject the claim. Remember, the claim is the status quo. The claim is that everything's okay, nothing's changed, and we failed to reject that. So, or not the claim, sorry, the HO is that, everything's a status quo. HO says everything's status quo, nothing's changed, everything's good. H1 in this case, which is our claim, says nope, something's different. Well, we failed to reject HO. That means we don't support our claim. Now, again, we don't say it's true or false. We don't say that HO is even supported in this case, to be honest. We just say that HO has been failed to reject. So basically we're saying we're not sure if it's different or not. We're saying right now that data you have right there, this data right here, does not give you enough evidence to be able to state that. You're going to need more extreme data to show that there's actually a difference. Now, again, this is the traditional method of doing it because you're comparing a critical value to a test stat. The other way would be to convert this into a p-score, which you can't do, right? You can get a range, but I'll show you how that would be done in this case. If I want to convert this into a p-score, into a p-value rather, I go to my table here. Let me erase this stuff here. And so I look for, okay, I'm at 40 degrees of freedom, roughly, because that's my best estimate. Negative 0.6 is my test score that I'm looking for. Well, if I go down this table here, negative 0.6, remember positive in this case because I'm looking for the positive version, will be all the way at the end here, right? 0.06. That's going to be all the way at the end of this row. So the p-value of this, if I'm doing it in two tails, because I'm doing a two-tail test here, the p-value of this is going to be bigger than 0.2, right? Because remember, as you go down the table, the p-values go up and up and up. So this p-value right here, and again, it's going to be true for the, I'm not sure why I put 0.06. It should be just 0.6. Remember, this is going to be true even for the negative version because t-scores are symmetric. But this value is going to have a p-value of more than 20% essentially. So if I go back to my table here, this p-value, this PV, is going to be bigger than 0.2, right? This p-value is bigger than 0.2. Well, if I compare that to my alpha is 0.05. Well, I may not know how big this is exactly, but if it's bigger than 0.2, it's definitely going to be bigger than my alpha. So I lead to the same conclusion. Because remember, if the p-value is bigger than your alpha, that means you do not have enough evidence to reject the null hypothesis. The p-value is a gauge of how well your null hypothesis looks. And in this case, it looks pretty darn good because my p-value is beating my significance level by quite a bit. 20% is quite a bit of a bigger jump, bigger than 20% actually. It's quite a bit of a bigger jump than 5%. So again, this will give you the same result. It's just a little bit more awkward to look up the p-value for this than it is to look up the critical value for your alpha. But either way will get you the same result. So that's it for this video. Hopefully you enjoyed it and helped you out. Again, very similar to the last video because all that's changing is that we're using a t-score rather than a z-score, but everything else is much the same. If you need any more help, let me know. Otherwise, have a good day.